Alright, so I think we would have seen this, so this is kind of familiar. So what do we know as purely resistive circuit? It basically just means that in your circuit, right, you only have a resistor, or it can be multiple resistors and all that. But all in all, it just basically means that it's only resistors in your circuit. That's why you know it as purely resistive. Alright, and you know, the simplest, most basic rule that we need to know for all circuit theory would be the Ohm's law, where V is equals to IR, right? So this is pretty much straightforward. Alright, for resistive circuit, current and voltage are always in phase. This is for purely resistive circuit, yeah, so circuit with all resistors only. You will know that your V and your I at any given point of time, it's always in phase. Basically means that they start and end at the same time. Alright, so V equals to IR. For you to get the VI, basically you just take the V divided by your R. If there are a combination of resistors here, you basically just sum all the resistors. That would be your R over here. Yeah, so that's for purely resistive circuit. Okay, don't think I need to go through very much on this part. Just as what we have discussed earlier on, so this would be what the phasor diagram would be. I think by now you would understand that why these are just horizontal alongside with our x-axis. Remember, your V and your I are in phase. There is no phase difference, and therefore your at any given point of time, your I, your V, it all just lies along the horizontal axis of your x-axis. Alright, for purely resistive circuit, very important. Alright, so I think the important thing is just as long as you understand the concept from earlier on, so this is pretty much kind of related. Okay, so if you want to get the power, alright, what do we get power? Power is basically P equals to V times I. Alright, so in this case they just indicate it with VMIM. Alright, and if you want to get the average power, you just basically divide it by 2. That's it. Very much straightforward, right? So P, or your power, is equivalent to V times I. Alright, so this is whatever that we have seen earlier. Okay, alright, so P is equals to VI, right, the voltage times with your current, unit in watt, very very important. But we do know, right, because V is actually equals to IR, so if you replace V, alright, with IR, so you will have I times R, and that's where it gives you I square R. Alright, similarly, if you go by VI over here, and you know that I is actually V over R, right, based on your Ohm's law, V over R, this is VI, I being represented with V over R, so this will be V square over R. So sometimes it literally depends on what you are given in your question or your circuit and all that. You might not be able to just use VI. Sometimes you will need to use I square R, or you need to use V square over R. So it depends on what you have at a given point of time. The unit will stay the same. Okay, so let's move on to the next one. For inductor, alright, so this is the symbol of how inductor looks like. Alright, it's like a mini slinky kind of thing. Like for resistors, it's like a zigzag thingy, right? So this is inductor. Alright, so it's a property of conductor which causes your EMF. EMF is kind of like your generated voltage, alright, to be produced by change in current flowing in. So usually inductor also, in this case, when we want to generate electricity or AC voltage and things like that, then you play around with the electromagnetic induction and stuff like that, and that's where your inductance will be present. When do you use this? Alright, sometimes we use this inductor, all right, when we want to control, because if you look at it, right, it's kind of related to change of current. So at any point of time, sometimes we do need application with current being changed and things like that. We want to be able to control a certain current in a circuit. All right, so it's definitely being used in electronics. You see, for example, like switch mode power supply, as power energy storage device, transformer, you know, where everything that is related to electromagnetic induction and so on, it definitely will involve your inductance. All right, you also use it for communication. Okay, so that's just part of how it is. We have looked at this. All right, so for a purely inductive circuit, it just basically means that your circuit is just with inductance, right? So your voltage across your inductor, being denoted as VL, is equivalent to L di over dt. All right, long story short, all right, you know that cos is actually also equivalent to sine omega t plus 90, and therefore they come up with this as the simplest term, V sine omega t plus 90. All right, plus 90 here is true for all purely inductive circuit. Basically means that if your circuit is all inductance and all that, you always have plus 90 over here. How you get your V? It's actually omega Li. All right, L being your inductance being in your Henry. All right, the unit is Henry, and this is your I. All right, so the faster the current changes, the larger the induced voltage. So that's just how the property goes. Okay, so this is how it looks like for inductive circuit. Remember, you have a plus 90 just now. So usually you have everything like for inductive circuit, your current is actually lagging your voltage by 90 degree. So if you look at it, right, this is your current and this is your voltage. If you extend this somewhere further and all that, if you extend this somewhere and so on, all right, you get to see that this actually starts way earlier compared to this, and it literally means that, right, because current lags voltage by 90 degree. So this literally means that the difference between this side, all right, how I know from this side to this side, because this is where my current wave starts, this is where my voltage for VL starts. All right, where it starts, not by here. All right, I'm not comparing with here, because why? When we want to compare two waves or two sine waves together, we always compare it at the point where both starts at the same point. Like for example, this starts at 0, this starts at 0, then we do the comparison. So this basically means that the current is lagging by 90 degree. Okay, and when we draw it out and all that, you know that the V is of plus 90. This is my I. All right, this literally means, remember just now when we talk about any reference voltage that is leading, so which means it's a plus, right? So it's actually on top with reference to the horizontal line, right? So anything that sits on top and all that literally means that it's leading. All right, so this also means that your voltage leads your current. By how much? Because this is perpendicular for purely inductive circuit, it's 90 degree. Or in other words, if you just say it in a reverse term, it means that my current is lagging my voltage by 90 degree. Okay, so that's about it. And over here, instead of R, right, R is for resistance, so XL here is reactance for my inductance. We just call it a different term and all that, but it's actually the resistance faced by the inductance. All right, but we call it as reactance. So V over I as well, only that your XL is actually 2 pi FL. All right, so important for us to know this term here.